Continuing on with vibrations, week 1. I believe this is video 9, which seems like an excessive amount of videos, but there's going to be even more. We're continuing on with periodic motion. I believe I've numbered this like where it's represented in the book. What is periodic motion? And I'd say motion that repeats itself with time. So I go motion that repeats itself with time. So it could be not just like a pendulum or a vibrating spring mass. It could be like the bus, right? Of like a bus route, right? As opposed to harmonic motion, which usually means something that's like a sine wave, right? Similar to a sine wave, a motion that can be described in terms of sine waves, sinusoidal waves, in terms of sinusoids. There you go, sinusoids. Sinusoids. Like a spring and a mass. So here's some nomenclature things, so the difference in these different graphs. So this first one up at the top left, the difference is, these are difference in amplitudes, right? So there's the amplitude of that one, and here's the amplitude of the red dashed one. So different amplitudes. Different amplitudes and attitudes. Here you go. This one here is a difference in frequencies, because you can see that it has different. You see where it crosses. Like here is one cycle for this guy, but here is one cycle right here for that guy, right, for the dash line. So here we go. These are different periods, and therefore they're different frequencies. One thing to note, though, is it appears that one of them is twice the frequency. No, it's related. It's not quite twice, but it's related. It's like 1.5 or something like that. So at some point they're going to like cross each other again. It's interesting to note. And so they're kind of some amount complicated. Here's one where we have, you can see the starting point is different. So this right here, these are the same frequencies with the same amplitudes, but they're different phases. They're out of phase. I don't want to use the word out of phase, but they don't have the same for phase. And over here, though, you can see that they're 100% out right here. This is 180 degrees, or pi, out of phase. So I can say that these one over here on the left is out of phase as well. These are important things to recognize in terms of this sinusoidal motion. So we got our man Fourier. And here's an interesting website right here. I'll put a link into the thing, the Fourier transform. This guy really loves Fourier transforms. And a Fourier transform. First off, let's take a look at this. This is like an approximation of a sawtooth, right? So you might have a signal that you want to generate that looks like this right here, with like a almost I guess like a vertical right here and a ramp up, and then a vertical, and then moving on right here. And here's one period of that. And if you wanted to represent a signal like this for whatever reason, and oh, by the way, like old-timey synthesizers, and the kind that kind of came back as sort of a retro type of sound, they would make like a sawtooth type of thing, or on a tremolo pedal if you're a musician. Actually, that's one of the different shapes that you can have for the volume control on the tremolo, is to have a sawtooth type of thing. A bunch of different phases. But anyway, if you wanted to represent that, you could do that using the concept behind the Fourier transform. The transform is a means of representing or the idea, representing any signal, it's not any, there you go, any signal as a combination of sines and cosines, right? And what is it for? Well, okay, because we could take a signal and try to represent it by sines and cosines, we could figure out what kind of frequency and amplitude content is available there. And so we can find the frequencies within a signal. And then otherwise, we could move for what's often called the time domain, which means we track something, a signal versus time, to the frequency domain. So convert time domain into frequency domain. It's like a spectral analysis, frequency domain. Basically, we see what's the repetitions that are like within something, and by doing that, we're. By the way, this is the fundamental thing, but it's not a practical matter for everyday signals to have to do the mathy thing. So we have something called a fast Fourier transform, which can be done in all kinds of different programs. And it can be done in MATLAB, probably with what I would prefer to use over like Python or other things. But we can convert into take a signal of many different types of things and convert it into the frequency domain. How does it work? Well, it works from the magic of convolution. Now, you don't necessarily need to know this, but there's lots of other means of trying to explore signals and data processing, and convolution is at the heart of most of them. What you're basically doing in convolution is you're taking a signal and you're passing it by a known signal, a known wave, or it could be a sine with a particular frequency, and you're passing it along a signal, and every time that they match each other, boop, you get it's like an on switch. And because of that concept, you could do that with sines and cosines, but you could do that with the other things called like wavelets, which are like little partial little things, little blips. Like there's one called the Mexican hat that looks like that right there. I used one called the harmonic wavelet, which looks like this right there. I probably did a bad job of that, but right there. But it has little squiggles and it dies up. But you're able to, with those, to be able to fix some of the defects of just taking a Fourier transform to a somewhat changing signal. But anyway, the reason why you're able to do that is the same principle that Fourier transform works, which is called convolution. I don't know if they teach that in class, but it's a good idea. Boy, this is a lot of mathy stuff that's right in there. But this is the Fourier transform. I'm going to continue on this because you don't necessarily care about this. I'm not going to spend that much time in class on it because I've already saturated you and the first class. But a typical, so this is a typical form. The typical form of the Fourier transform. Of a Fourier series is what we call it, right? So you have this guy right here is usually the average of a signal, and then here's with a particular frequency, here's the associated magnitude that you would find. Here's another frequency and the associated magnitude that you would find with as it relates to the cosine of there, and then there's the same thing with the B, and there's that frequency, and here's another, okay, and you can see that it just keeps going on with time. Here I've written it a little differently because this is just a single frequency, and we might use this form when we know that there's only one principal frequency and its multiples are available. So when doing a problem, that's the one that I usually would go to in there, just to try as an example. And the main goal is, when we're coming around here, is to find these coefficients. Notably, this first coefficient is usually, some people think of that as the DC part of it, which is to say, if you have a signal that's like up here like that, it's this guy right here. It's the how far off of the axis does that thing move. That's okay. And so the rest of it is just trying to capture the magnitudes that are needed for these coefficients at these various at the different frequencies. One benefit to trying to approach this on a signal is that you can change. You have some choices of where you make your integration across. So if it's a discontinuous thing, like a square wave, you could just pick where you want to do the integration. There's a bunch of rules, other things that you would note. You note that like things that are, some signals are considered odd signals, and that gets rid of, I believe, all the B's. Or some things are considered even signals. That means that they're like really kind of symmetric, I believe, across the Y, at the boundary. Like so, they like that right there, right there. They're a mirror image, right? Thing, and those are considered even. And then you don't have A's to simplify the thing. So I already mentioned the convolution. These are convolutions are like on-off switches, right? And so here's like the principle right here, like when this frequency doesn't match that frequency, it equals to 0. But when they do, you could put in this value. So here are the on-off switches, which are the part of convolution that makes this problem. And here's the important thing that you want to know. Nobody ever does this except in an academic exercise to demonstrate where it comes from. What they really do almost always is a fast Fourier transform. There's something called a discrete Fourier transform, and you might find that you get into research and that kind of thing, and you might do that type of thing. But the fast Fourier transform is very much the most common data processing tool that we will get right into there. And so here's an example, and I'm continuing on with this video, even though, and by the way, I don't know that this is included in this course, by the way. I'm not sure if we're doing fast Fourier transforms. Maybe that's vibration 2 or in the acoustics class. But just be on alert that like this is, when we're talking about signals and signal processing and vibration signals, the Fourier transform is an important concept. And it shows up in this book, but I'm not sure we're using it. Example that you don't need to know, but it can't hurt. Okay, so here I've made this. So here's a square wave, and I worked this through when I was at the other university. You'll notice that this does not pass through 0 all the time, that its maximum is 3 and its minimum is -1. Also notice that its period is 4 as part of this. So you could see by doing this integration that's up above, it goes 3 between 0 and 2, and then go 1, and then it goes -1 is what happens here between 2 and 4, and what you end up is getting 1. But you can do this in your head because that's the average, right? So that's what I had said about AO. AN here is the equation that we would put onto the thing, so it's the function times the cosine, and we are simply, I guess we're using through N, right? So that's going to be through N is going to be like whatever period that you happen to be going through. So the first period, well, no, actually, you see from right here, after doing this, that AN is always 0. I can't remember if this is considered an even or an odd function, but because it's symmetric, it's one of the two, or it's non-symmetric. Bn being applied to the same thing, we do, once again, between 0 and 2, and 2 and 4, so it's discontinuous, and here's the function is 3 and -1 into there, and we're able to get the Bn is going to be equal to, just plugging the numbers in and doing the integration. We get, we notably down here. So when n is even, Bn is equal to 0. When n is odd, Bn is equal to 8 over pi n. That's what this says right there. Wouldn't necessarily want to play around and do this integration myself. I've done it before, but didn't like it. But you could go ahead and put that value in there and find what B1 is going to be 2.546, B3 is 0.848388, and so on, right? So what does that mean? Well, what you could do now is you could put these B's back into this function right here, and you could slowly, you'll see as we add them together more and more, you're going to be able to replicate this signal, this square wave, using sine waves. I believe that's true because I think all the cosine waves have A's in the front of them. So we only have B's, so it's the sine waves that are working here. So here is the sine wave. So if you plug time into there, here's the red sine wave that you get. If you add in the other guy, this next guy is 0.8488, you start to get this right here, this shape. If you plug in the next one, the 0.5093 times the sine of 10 pi over 4, you get this shape. You see that it starts to get closer and closer to a to the square wave, right? So what we've done is we've replicated. See this equation right here. Let's see, make it clear. That equation replicates this. If we instead use the FFT, and it doesn't quite work out perfectly, of MATLAB. This is a MATLAB FFT, and it's not hard to do. I can put in the code, at least what I have in there. I'm not quite getting the magnitudes that I expect, but I do get the frequencies, right? So what I've just done is I've entered in a chain of signal of, of time and X, like right here, and I've created it, right? So it went like 0 and then 0.1 and 0.2, blah, 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 or something along those lines. And then when it got to like 2 and then 2.1, dot, 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 dot. So this was like, I had, 3, 3, 3, and then it got down to here and I got -1, bop, 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 right? So I had the string of signals and I hit the FFT command essentially, when there's a little bit more to it, but it pumped out a graph that shows me the frequency, and you can kind of see what those frequencies are going to be. They are periodic, and they have what did I say up here? So they had they had a period of what did I originally say? I think 0.2. What did I say? Oh, no, they had a period of 4. So you would expect that they would have a frequency of 0.25. And so here it is right there. Yeah, 0.25. See? And then, of course, there's it doesn't have twice 2.5. It has 3 times, so it's got 0.75. And I guess it was, is it 5 times it? I guess it's the 5 times the thing, right? For that. And then the magnitudes aren't really matching that closely because I would kind of expect some of those to like look closer to those, and they don't quite. But most of the time, when I've dealt with spectral analysis, it's the relative magnitudes of these peaks as opposed to what their actual. So there you go. That is a lot of information, and maybe it's worthwhile, maybe it's not worthwhile. We'll see. We're going to go do some other examples, and I forgot how many videos this was. It's too many videos. We'll see in the next one.